Record, and yay. Okay, so the unit step function, two conditions. It is 0 if t is less than 0, and it's 1 if t is greater than 1, and it is changing if t equals 0. We call it a unit step because the final value is 1. Okay, now things we may want to do. We may want to model going over and turning on our 5-volt voltage supply. And then, so I may want to turn this on and have this be 5 volts. I may want to turn on one supply and then 1 second later turn on another supply. So I may want to move when it happens in time a little bit. So different things we can do with this. We can go from 0 to 3 volts at t equals 3 nanoseconds. So this would be 3 times u of t to get the 3 volts. And I would have to put that time step in there. It would be, it would be t minus 3 nanoseconds. Because if I plug in t equals 3 nanoseconds into that equation, I get 0. So then that's where the step occurs. If I want to go from 1 to 2 volts, well, I'd start out at 1 volt, and I'd add another volt, and that would be u of t plus 3 nanoseconds. This is where you got to be careful with your S's. A lot of times I just start doing this, so we know it's not our variable S. Okay, so a lot of things we can do with the unit step function. Things that change, things that get switched on and off with time. This is the impulse function.
Can you go back for a quick second, please?
Sure.
Thank you.
Okay. Now, the impulse function is 0 if t is less than 0. It's infinity, should put commas in there, if t equals 0. And it is 0 if t is greater than 0. Yeah, that I just really don't want to have to build that circuit. We can't do that. We call it a unit impulse because it has a magnitude of 1 infinity. Yeah. If I wanted a unit impulse function, and if we, amazingly, I got into an argument with Colt, and you just have to know Colt. He wanted me to prove that the integral of this function was 1. 2 hours later, we convinced each other. Yeah, it really is. You integrate infinity at 0 time, and the integral is 1, and we'll just accept that because we're not mathematicians. So the integral would be the area. So this has an area of 1. Now, if I wanted an impulse function that has an area of 12 amps, that means the pulse was a total of 12 amps across all time. At 6 nanoseconds, what I would put in is 12 delta of t, and it's at positive 6 nanoseconds, so it's t minus 6 nanoseconds. Okay. Except that one, Dr. Apka or Dr. Seven or Dr. S, or whoever teaches you 348 will love the impulse function. I think it's ridiculous, but I'm a circuits person. I'm not a communications person. Not that mathy kind of, okay. This is a ramp function. So this is the third one we're going to talk about. R of t is 0 if t is less than 0. It equals t if t is greater than or equal to 0. You can make that equal sign go either way. It's still 0 at time t equals 0. We call it a unit ramp function because it has a slope of 1. And if I wanted a unit ramp function, which goes 0 volts, oh great, 0 volts until t equals 2 nanoseconds, then increases linearly, I'm gonna have to draw the graph. It's 0 volts until 2 nanoseconds, and then increases linearly and has a value of 10 volts at 7 nanoseconds. So there we go. So the slope of that line is it takes 5 nanoseconds to go up 10 volts. So it is 2 volts per nanosecond is the slope. Okay, so that's the slope. It's delayed by 2 nanoseconds. So it's going to be an R of t minus 2 nanoseconds. That's for the delay. And the slope is the thing out front. So it's 2, and we're okay with that as long as we put units somewhere, volts per nanosecond. So that would be that function right there. Without units, you might be off by like 9 orders of magnitude, because I would assume volts per second. Okay. 430. Yeah. Okay. I can describe a lot of arbitrary functions as being linear combinations of these unit singularity functions. What I'm going to do here, let's do this graphically. I got a question. Good. Maybe. Would you delay? Yes. I'm not too sure what you mean by these. So the way, okay, so generally, let's say, let me give you an example of something that would produce this. Maybe that'll explain your question, Jordan. I've got an op-amp circuit that takes a certain amount of time to go up to its final value. So it's linearly ramping up, and then it saturates and it gets to its final value. So that would be something that would produce a response like this. It's saturating at its 10 volt supply. I'm going to divide this graph up into pieces. Let me give myself lots of room for this. So I'm going to say the graph I've got there is the same thing as this, plus this. If I add those two functions together, and that's going up to 10. If I add those two functions together, I should be able to get that final function. One is just, oh, and then this goes to 0 at every point in time. So the first function looks like a ramp. In fact, I'm going to say this is R, it's 5, it's got a slope of 5, 5R of t minus 5R, yeah, that's not right, R of t minus 2. So that would give me, so let's figure out what I just wrote. Here's 5R of t. 5R of t minus 2 would be like this. So we'd have to subtract off another 10. That would be this first piece of the graph. I don't do this as much as I used to. The second piece of the graph, this is 2, is just simply 10 u of t minus 2. So we've divided it up into two functions. If we wanted to take the Laplace transform of this, we could just add 1 and 2 together. So add the two functions together, take the Laplace transform. We don't know how to do that yet. Let's go back and why didn't I just delete that slide? I never mind. Okay, we've got these three basic functions. We've got u of t. If I want to take the integral of this, I remember taking the Laplace transform, I'm taking the integral of f of t e to the minus st. Our bonus here is I'm only integrating from 0. And at time t equals 0 to t equals infinity, that function is 1. So I can replace the u of t with 1. And I'm integrating e to the minus st. I may actually do that integral from 0 to infinity. So that would be 1 over minus s times e to the minus st evaluated from 0 to infinity. At infinity, e to the minus st is going to be 0. So it's 1 over minus s, 0 minus, and at 0, e to the 0th is 1. So I get 1 over s. The Laplace transform of that step function's 1 over s. Number 2 on the table, the Laplace transform of u of t is 1 over s. This is my key slides. Laplace transform table. I could do the same thing if I had a decaying exponential. That's a really easy one too, because now this just becomes e to the minus alpha minus s times t, and you get something that looks like 1 over s plus alpha. It's always like that. We don't have to perform that integral every time. We can look it up in the table. MATLAB can do it for us. The integral of delta t is 1. And I will just declare that. Okay. So people who like math much better than most engineers do have gone through and actually done these integrals for a whole lot of different functions. And every function that we'll do on the homework or we'll do on an exam will be on these tables in one of my key slides. So here is a whole bunch of different transform pairs. One thing to note, that these transforms are only valid for t greater than or equal to 0. We've lost the information about t less than 0. In the domain that I'm to care about, where t is greater than 0, u of t equals 1 in the Laplace domain. That's important because sometimes to make things mathematically correct, I will extraneously just add a times u of t at the end of the equation. All I've done is multiplied by 1. Because in the domain we care about, it's always 1. Here's the one that gets everybody. And I know, and you pay attention to this. What is the Laplace transform of a 5-volt source? It's not on this list. 5, 1, it's not on there. Okay, and yet I will throw it on the exam and people will just hate me for that. Or I'll throw it on the homework and you just send me an email, ask me a question, or come by my office hours. 5 volts is, since our domain is 0 to infinity. 5 volts equals 5 U of t. I told you I can extraneously add or ignore U of t's whenever I feel like it, because it's always 1. So the Laplace transform of 5 volts would be the Laplace transform of 5 U of t. It would be 5 over s. I don't make up these rules. Uh-oh, I'm in trouble now. You can just yell at me, it's more convenient. Wouldn't it just be 0? No, it's not 0, because it's, if for time t greater than 0, it's 5. And I don't know anything about what happened in the negative time domain. So I can pretend it switched on at time t equals 0, or I can, even if it was on for all time before that, I don't know anything about what happened before time t equals 0. Because my domain is only time t 0 to infinity. Uh-oh. In trouble. Okay, good. All right. So this is one set of Laplace transforms from one book. Here's another one. The ones that this one had, wait, let's look at the first one first. It has the delta, the u. It doesn't have r of t on here. It does have the ramp. There it is, t. It's got exponentials. It's got sines, cosines, t e to the at. It's got exponentially decaying sine waves and exponentially decaying cosine waves. Pretty much almost everything that you would like to use. But, and then here's another table. It's got much of the same stuff. It includes, what is the big things in here? It's got t to the n e to the at. And it's got sines and cosines with a phase shift are the things that got added there. The theta is just an arbitrary phase shift. Okay, that's not so bad. Use the tables. You don't have to integrate this times e to the minus st. You know, just don't do it, okay? If you get a function, it won't happen on the homework, but if you ever get a function that you don't know how to take the Laplace transform of, there's this amazing thing that you guys have now that were not around when I was in school. There are these web calculators. They will do integrals for you. They will do derivatives for you. They will, yeah, just make sure you know what you're putting in there. But I wouldn't, anything that's going to be on the exam, it's going to be off of one of these two tables. Now there's also properties of Laplace transforms. One of them so ingrained in your mind that you don't even realize I'm using it. If I multiply by a constant, the Laplace transform of 5u of t is going to be, the Laplace is going to be 5 over s. They're linear, thank goodness. Okay. If I take the Laplace transform of things that are summed together, I get the Laplace transform of each of the pieces, and I just add those up. The first derivative of time, and you'll use this in 325, and you'll use it a little bit in the 280 lab, and I'm sorry, but if I want to take the derivative of a function, the derivative of f of t with respect to t, I can do this without doing calculus. This is why I like these things. The only reason why I got through this is, instead of taking the derivative, I just multiply it by s, find the transform of the original function, and subtract off the initial condition. So taking derivatives is like multiplying by s. If I want to take the second derivative, I multiply by s squared. Third derivative, s cubed, and it goes on. Integrals. I want to take the integral of a function with respect to time. I don't have to integrate it. I just divide it by s. Find the Laplace transform of the original function and divide it by s, and I'm done. This translation in time we'll talk about, it's messy. Let's just save that for later. Okay. This one we're going to do today too. We're going to do this one today. Yeah, we should get there. So let's just do some examples here. Now I've got this function in time. All we're going to do is just Laplace transforms today. We'll do the inverse on Wednesday. I look at my table and it tells me that the Laplace transform of delta of t, and I'm going to use this symbol to say just transforms into, is 1. And the Laplace transform of u of t, and I'm just looking these up off the table, which is in my key slides, is 1 over s. And the Laplace transform of e to the minus alpha t, which is what was in my book. It probably says a here. Yep. E to the minus alpha t is 1 over s plus alpha. There's a sign change there. This was a negative sign here. It becomes a positive in the transform. Okay. So I want to take the Laplace transform of this 3 things added together. I'm going to use linearity. F of s is the transform of delta of t is 1. The transform of u of t is 1 over s, so that would be 2 over s. Minus 3, and this is e to the minus at becomes 1 over s plus a, so over s plus 2. Now, having taught algebra in high school, believe it or not, that was my punishment for all that ignoring math when I was in it. What I'm going to do here, and I know it's useful for later on when I want to do the inverse Laplace transforms. I'm going to clean this up and put it over a common denominator. So I would have to multiply the first term times s plus 2. The second term, I would multiply the numerator and the denominator by that. The second term, I'd multiply the numerator and denominator by s plus 2. And the third term, I'd multiply the numerator and denominator by s. So I get s squared plus 2s plus 2s plus 4 minus 3s all over s times s plus 2. Just put it over a common denominator, group like terms. This is, I'm just going to throw it over here because I have room. S squared plus 4s minus 3s is plus s plus 4 over s times s plus 2. That's a really convenient form to have it in because a lot of times your next step is to invert that. So put it over a common denominator. And there it is. Yeah, I got it right. Yay. Sometimes I make a lot of sign errors. If you want to know what to catch me on. And polarity errors and things like that. So we've got another example here. We've got f of t equals cosine 3t plus e to the minus 5t. I look at my table and cosine of omega t is going to transform to s over s squared plus omega squared. And I've got e to the minus alpha t is going to be 1 over s plus alpha. But I don't have anything that has cosine times u of t. So this is a case where I'm just going to ignore u of t because it equals 1 during my domain. So I can ignore it when I want to. And I can add it in when I want to. There will be a place when I extraneously add it in, but we'll get to that later. So I just find the Laplace transform of cosine of 3t. And that would be cosine omega t is s over s squared plus 3 squared is 9, plus 1 over s plus 5. And again, I want to put this over a common denominator. So the first one I'd multiply by s plus 5. And the second one I'd multiply by s squared plus 9. And then it would be over s squared plus 9. This was the part everybody hated in Algebra 2. S plus 5. It's an algebra mistake waiting to happen. I'd be surprised your calculator can't do this. So I have 1s squared, I have 2s squared. I have 5s, and I have 9.
Can't you just cancel the parentheses?
No, because the
Oh,
parentheses,
yeah.
yeah, they're not multiplied by the whole thing. They'd have to be like, yeah.
Okay, never mind.
Completely
Thanks.
factored out, yeah. Okay, there we go. Stupid algebra tricks from Algebra 2.
Can you explain how you canceled out UT?
The U of t, okay, so the U of t, I'm going to take the Laplace transform of this. And when I do the Laplace transform, I'm integrating the function from 0 to infinity. And from 0 to infinity, U of t equals 1. So since it just equals 1, I can have the U of t in there, or I can ignore it.
Oh, okay. I see what you're saying. You're just kind of just multiplying it. All right, cool.
Yeah, it's kind of a weird math trick, and I will get much less mathy after exam. We can break out the lifesavers. We can go back to doing electronics. The person who taught me this class was this very proper Southern gentleman named Dr. Rogers, and you never called him anything but Dr. Rogers. And this was 2 classes for me. We have around the quarter system. So the second part of this class was my electronics professor, Dan Shavar, and he was a little bit crazy. He was a physicist from University of Chicago, and he had all these little offbeat stories he would tell about how electronics worked that had nothing to do with electronics. That was so this is me channeling Dr. Rogers. Wait until wait until after the exam. Okay. Dan Shavar was great. So we got that one, and I got that one right. Yay. Okay. So here's another one. We know we can ignore the U of t. So all I got to do is look at the table for something that looks like t cosine 3t. Is there one in here? No. Uh-oh. What are we going to have to do? Well, we have one that looks like this, cosine omega t. Cosine omega t is s over s squared plus omega squared. And I'm going to have to go to the properties. I have something that looks like this. T f of t. Well, my f of t could be cosine omega t. If I transform that, oh, I hate this problem. You'll see why in a minute. I have to do calculus. df of s ds. So it looks like multiplying cosine 3t by t means what I have to do is I have to find the Laplace transform of cosine omega t and then take the derivative of that in the frequency domain. Yuck. Okay, I know how bad this is. Cosine omega t. So cosine 3t would be s squared plus 9. And what I have to do now is take, oh, that's an s. I have to take the derivative of that with respect to s. And I go to my calculus book and I look up the thing.
So why wouldn't you just multiply it by? How come you wouldn't break that apart and substitute 1 over s squared for t?
1 over s squared for t.
For your Laplace transform first?
I have to transform it. Okay, the property, what the property is saying is that if I multiply some function by t, and I want to take the Laplace transform of it, I have to take the derivative of the Laplace transform of the original function.
Okay.
It's, yeah, I'm not going to go through, I don't want to prove that. I've just accepted this. The people who will prove that will be whoever teaches you EE280 Feb. I'm sorry, I'm a circuits person. Okay, so I have to take the derivative of this mess. So I go and I say, I don't remember the rule. But remember this one from calculus, the u over v prime, and there's a sign in error I will make in here if I don't look it up. It's ud, oh, I can't even read that, vdu minus udv. Oh, because I fixed it on the other one. I know what I did. It's got to be vdu. This was before I was putting tails on my u's so I could read this. V squared. So we find the derivative and we go through and we do the calculus part. And the details are actually in the slide solutions, but I don't want to bore you to tears with this. When I do this, it comes out to be s squared minus 9 over s squared plus 9 squared. Okay, so when you multiply by time, you've got to take the derivative, you have to find the Laplace transform of the original function, and then take the derivative of that in the S domain. Yeah, I got it right. Okay. Now let's look at something that you can recognize as being a little bit more useful. I want to pulse something on and then pulse it off for a short amount of time. This is kind of like that graphing function I showed you earlier. We could think of this g of t as being the sum of something that comes on to 10 volts at time t equals 2. I'll just say that's in seconds. Somebody didn't label that. We'll say this is in volts. Plus something that goes off suddenly goes minus 10 at time t equals 3. If I add those two functions together, I will get what I have there. So my g of t looks like 10 u of t minus 2 minus 10 u of t minus 3. So that will give me a 10 volt pulse for 1 second. And I can mathematically model that function. Some functions cannot be mathematically modeled, which are most of them that you actually use in the real world. When you see real world signals, they don't look like mathematical functions. We don't use Laplace transforms for that. So I have to be able to put it in a functional form. There's a wonderful thing, there's a close cousin of Laplace transforms called Fourier transforms. And with that, you can actually transform data into the frequency domain. And you can push the button on the test equipment, do a fast Fourier transform. It's great. MATLAB will do it. You can have your microprocessor do it for you. All those wonderful things. Laplace transforms are a way to get to Fourier transforms, as far as I'm concerned. Okay, so that is my G of t. Now if I want to find G of s, I just have to transform the parts. We already know U of t is going to be 1 over s. Oh, there's something new coming in here. The other thing is we have this translation in time. No, don't tell me it's not bad. No, it's not. And the translation in time, we're not that bad yet. I was hoping not to get to this one today. F of t minus a, U of t minus a, and a's got to be greater than 0, is going to transform into e to the minus alpha s. Oh, it must be 5. F of s. The beep was reminding me I had an IEEE meeting tonight. Okay. So my f of t here is a constant, so I don't have to worry about the time shift. When I shift this in time, it's the same thing as taking the Laplace transform of u of t, which is 10 over s in this case, but I have to multiply it by e to the minus time shift s. And I do the same thing over here. And it's already over a common denominator.
Why do you subtract the like the second pulse from the first one? You just didn't like general.
Because if I didn't subtract the second pulse off, this graph would be 10 for all time. So once it gets to time t equals 3, I want to subtract 10 from it.
Okay.
Yeah. Okay. How much more do I have? There we go. Probably not. Let me just look ahead. Oh, yay. Okay. This is another signal that you might see in the real world. I've got a digital clock. I've got something that's pulsing continually with time. Okay. The new property we're going to use is that f of s equals f1 of s, where f1 of t is just a single pulse. Get started on the homework for this. You can do the first half of the homework, and then you can have questions for me tomorrow or on Wednesday, because this is kind of a long homework if I remember. You can do the first half of it, the second half, but not yet. T is the period of the signal. The period that it repeats on. Okay, so the first thing we have to do, looking at this, I need to find the Laplace transform of the single pulse, and I need the period, and then I can get that. So the single pulse would be u of t minus u of t minus 2, just like the last one. I want it to go up to 1 at t equals 0, and I want to subtract off 1 at t equals 2. And then I can describe that pulse. In the Nilsson and Riddell book, if you're having trouble with this concept, they have like 3 or 4 pages on this, and they call it the windowing function. They talk about, basically doing the same thing I do, only probably more mathematically correctly. I just do it and get it right. So now we want to take the Laplace transform of f of t, f1 of t, and that would just be 1 over s plus e to the minus 2s over s. So that's already over our common denominator. Our period is how long it takes to repeat, and it looks like it repeats going 0 to 5 to 10. We get the leading edge, so the period is 5. So then I just plug everything into the formula. Yeah, is 1 plus e to the minus 2s, and the s is in the denominator, and then I multiply by 1 minus e to the minus 5s. So you can actually take Laplace transforms of periodic pulses, periodic signals, anything that's going up and down, anything that looks like a sine and cosine, an exponential, a exponentially decaying sines and cosines, and frequency and phase shifted sines and cosines. Then the math starts getting messy. So we don't do that anymore. Okay, we got that one spelled out. Last thing I'm going to talk about, well, next last thing I'm going to talk about, and then we can go home, and this is just one slide, is the initial and final value theorem. This is really important. As engineers, you worry about stability more than anything else. You want to have some kind of mathematical assurance. You may be wrong, but you want to have some kind of mathematical assurance in the back of your head before you plug in your system that it won't blow up. This is job number one. When things blow up, lawyers get involved and it's no fun anymore. Okay. So one of the things I want to be able to do is estimate, first of all, what is this is, remember, this is in the time domain. When I first plug in the system at time t equals 0, is my system going to be at infinity? Am I going to be at some singularity, or is it going to be at 500 volts that's going to blow the whole thing up, or whatever? I want to know what my system's going to look like when I plug it in, and I want to know what my system's going to look like if I plug it in and walk out of the room to go get a cup of coffee and come back. And that's time t equal infinity. So we can do that directly from these Laplace transforms. To find what it's going to look like when I plug it in, I take the limit as s approaches infinity. Now this is h is 0, and the limit as s approaches infinity of s times my transfer function. For h of infinity, I take the limit as s approaches 0 of s times the transfer function. So here's my initial transfer function, and I want to find out if it's going to be stable. I'm going to start out at infinity because this is the easiest one to do. I want to take the limit as s approaches 0. Notice that this went to s cubed because I multiplied the numerator by s, and then the rest of it stays the same. Well, if s is 0, the numerator is 0. I still have to check the denominator because it might be 0 too. And that comes out to be 3 times 25, 75. So this is 0. I'm okay. At time t equals 0, at t equals infinity, all the energy is decayed away. Nothing has exploded. Okay. Now when I plug it in at time t equals 0, it's the same limit, except for now I'm looking for the limit as s approaches infinity. The way I did it in calculus is I would have taken every term in there, I would have multiplied it out and divided every term by s cubed. And then all of them would go away. And then someone reminded me, like the first or second semester that I taught this, about L'Hopital's rule. You can do that too. You just take the derivative of the top and the derivative of the bottom, go on, and you get the same result. But if I divide everything by s cubed, anything, so this is divided by s cubed. This term s over s cubed, if that, as that approaches infinity, is going to go to 0. So the only terms that are really going to stay are the ones that are in front of the s cubes. So, and then the s cubed down here would be 4. Are you guys okay with that? Or you just took calculus? You're probably okay with that. 20 over 4, which is 5. If you need a longer explanation, I can do that. And it's also in the slide solutions all written out. And how did I do it there? I divided by s cubed, of course, because that's what I did when I was in calculus. My calculus teacher hated me. Okay. It was easier. Needless to say, I've managed to learn math. I'm vaguely learning how to program circuits. I'm actually taking EE310 this semester, not officially. I'm just hanging out in the class and doing the labs. So as much as I could do. I've learned cryptography since I've been here. I've learned all kinds of interesting things. If I tried to rely on the skills that I had when I got out with a BS degree from Auburn, I'd still be programming in Fortran. I still tell people that's my programming language. Whenever anyone asks me to program, I go, I'll do it in Fortran. And then they say, well, I'll go hire you a programmer. I would still be using TTL logic. My simulator would be nothing like multisim. What we had, we did not have card decks. I'm just about a year too young for that. We had this line entry thing where you'd put in your circuit. If I wanted to, I would have to label, I'd have to go through the pencil and label all the nodes and give them node numbers. And then write out a program that basically said, from node 1 to node 0, there's a resistor that equals 2k ohms. From node 2 to node 3, there's a voltage source equals 5 volts. You're literally just writing this stuff down like this, no pictures or anything like that, which is part of the reason why I hate programming. Because it was really bad when I was in school. I mean, no, it was, we had these things called line editors. This was before you had a GUI editor. If you mistyped one of the lines in your program and you wanted to change a character in the line you had just typed, you would have to go through and hit this like escape character, go back to line 2, and you'd have to type that out, but it wouldn't say go back to line 2, it'd be like U2 or something like that. Go up 2 lines, go to character 15, strike that out, and add at character, that is now 14, because I struck one out, this other character. And if you messed anything, I just garbled everything. It was easier just to start over. See, the life has gotten much better. But I relied on the skill. I've learned so much as an engineer since I left college that, you know, my whole thing's obsolete. That's the exciting thing, is that you're always going to be learning, and there's always going to be new stuff. And it's not going to be, when you're working, I got, oh, okay, a minute. When you're working, it's not going to be like you're solving all these math problems. They're going to give you, it's like when I'm coming at you with a fire hose, and I'm trying to teach you all of electrical engineering, which is probably like 10 different disciplines in 4 years. And you get it about that deep, because nobody knows what kind of job you're going to get when you get out. And when you get out, you're going to specialize in one area, and you'll understand that, or they'll give you a small job too, because you're a pup engineer, so they don't quite trust you yet. So they give you a small little job to do. You get good at that, and they'll give you other little jobs, and suddenly you build up an area of expertise, and you'll learn it. It's a lot easier working than it is being an engineering student. And it's a good field to be in because there's always jobs. I've got a meeting this week with TSMC. They want to hire 300 new grads in electrical engineering this year down in Phoenix, which means there's a lot of other companies who also want to hire new grads too, by the way. So there's good job prospects. It's a good salary. and you do have free time um, to do other things. Okay, so this has nothing to do with me. Oh, why I was there in 310? Yes, because I have a project to do. I have not designed an FPGA for 20 years. And when I designed my last FPGA, well, no, I designed custom ASICs that were gate-based. I used pictures, not words. I refused to use Verilog because I had to design everything down to like the transistor level on that chip. Yeah, I've got a project to do. I need to design a microprocessor, and I don't want to do it with pictures. Internships during the summer, there's a lot of them. There might be some at TSMC, but because the factory's going up now, they may not be a lot there. Micron hires a lot of engineers for internships. We've had interns down at NXP, down at Raytheon in Tucson, Microchip. You just kind of have to look around. Go to the career fair. They hire for internships there too. You know, even as a sophomore, I know people who've gotten in the summer between their sophomore and their junior year. And it's good because a lot of times they offer you a job, and a lot of times you find out this isn't what I want. You may find out this isn't what I want to do, but you've got some experience on your resume now, and your employers will look favorably on that. And I know most of the recruiters, because they used to be my students. So yeah, go to those job fairs, even if they're virtual. You can do it. Let's see, who do I have to check off? Elena dropped. Oh, sorry. And I think the other guy dropped. Brendan, are you here? Ibrahim, you need to come to class. Okay, Ibrahim's not. Okay. I'll see you guys on Wednesday. I'm probably meeting in 15 minutes. 237. It's down the hallway with the labs. Yeah, down at the end. Okay, I can stop recording. Stop share. Stop chat.